Welcome back. In previous lectures we discussed about the primary and secondary features. Now in this lecture you will understand that the importance of what we have discussed during those particular lectures on primary and secondary features. Now this topic basically is on active faults. So initially we'll try to understand the different type of faulting events, how they occur, and what are the different tectonic setting under which different type of faulting will take place, and then we'll get into the paleoseismic studies. But paleoseismic studies I'll talk later on in more detail, but we'll just look at first the what are the active faults and what are different type of faults and what are the surface manifestation of this type of faulting, that is the strike slip, reverse or normal faulting. So in nature, for example, if you have the compressional tectonic environment, then what we see is that the combination of the formation of anticline and syncline, and further if you keep on deforming further, then you will get into having the overturn folds, and finally what we see is the fracturing along the reverse fault or the thrust faults. So you will, this terminologies which we have been using about the reverse fault and thrust fault, this will become clear in this lecture. So we have usually what we see is the folded mountain chain, and within the folded mountain chain we have the displacements which are along the respective faults. So fault, if we take as a definition, then fault is a fracture in rock along which block of rocks slip past each other, and those fractures are termed as faults. And faults mainly occur as a zone called fault zone, and the surface along which the fault block moves or slips are termed as fault plane, and the surface expression, that is the manifestation of the deformation on the surface, which is in the form of elevated cliff exposed at the surface due to faulting, is termed as fault scarps. So these are the few terminologies which you will remember, because when we are going to talk more on details about the different type of faulting, then the surface manifestation will differ from one faulting environment to another faulting environment. So style of deformation under different stress, what you will see is basically if you are having extensional tectonic environments, then you are stretching the crust. So you are thinning the crust in practically you are thinning the crust, and one block will with respect to another one will move down. So this is the hanging wall, this is the foot wall, that is what we call the stationary wall, and which is lying on the inclined fault plane. And similarly, if you are having the compressional tectonic environment, then you are doing the shortening of the plates or the crust, and you are resulting the deformation pattern will be folding, and mostly you see formation or the development of the reverse fault. And in case of twisting or shearing, as a pure shear, then you are going to result into the bending movement, and along the horizontal plane you will have what we call the strike slip faulting. So these are the major three type of different faulting: normal, reverse and strike slip in different tectonic environment or different stress pattern. You are having tension here, you are extensional, then you are having compression, and you have shear. So strike slip faults mainly are those faults which accommodates horizontal slip between the adjacent blocks along the strike of the fault line. So, I will just give briefly the idea about what we are talking about, the strike and dip. So, suppose you have horizontally stratified succession. So, this unit will not have any strike or dip. So, you will not be able to measure the strike and dip of such layers, because they will be exposed horizontally. But if you deform this, okay. So, for example, if you are deforming this layers, then they are like this, okay. So, you have the folded layers, so this imaginary line, if you take, okay, that is the contact between the two limbs which are dipping away from one another. So, you are having the fold here like this. So, this will be your strike. So, basically we are taking orientation with respect to north. So, if you take the north, south, east, west, then you are measuring the strike. Suppose the strike is, with the help of compass, you come across that this is the orientation, and for example, this is around 45 degrees. So, then you can say that north 45 degree east. So, this will be our strike, and the amount of dip is the inclination which is measured exactly perpendicular. So, the inclination of this, that is your angle between the strike line and the inclined plane, which is measured perpendicular to that, will be your dip. So, this angle will give you the dip, amount of dip, and the direction is the dip direction. So, for example, here if this is if we take this strike of this bed, this one is north 45, then the amount of dip is going to be, for example, you are having say 10 degrees or 20 degrees, then you will say 20 degrees dipping due east. So, this will be the amount of dip. So, any displacement which is taking place along the strike, then those faults have been termed as strike slip faults. So, strike slip faults, mainly you will find that if you are having the horizontal or the strike of any fault, then a block which are moved, for example, this is, I will draw a block diagram here. Then this block has moved towards us, okay, and this has moved away from us. So, this will be termed as the movement has taken place or occurred along the strike, where two blocks are just passing along this with respect to one another along this fault line. So, this is termed as right lateral, and if it is on the other another direction opposite to this, then we term that as an left lateral strike slip. We will come to this examples in coming slides. So, let us move ahead. So, again, strike is an imaginary line which is drawn with respect to the inclined plane and So if you have this one, then this will be, you can have the imaginary plane here. For example, I'll draw again. So if you are having this is your imaginary plane, and the intersection of this will be your strike direction, and the dip will be this one. So in nature, what we see, the dip, the movement is taking place along the strike and along the dip plane. So based on this, the faults have been classified. One is a strike slip fault that accommodates horizontal slip between the adjacent block along the strike of the fault line. Then comes the dip slip faults. So dip slip faults are the faults that accommodates translation or slip upward or downward along the dip of the fault plane. So you have, like, if you are having undisturbed unit or the layers, and this is your surface, and if you are having, for example, upward movement, so if you take this fault here, and then if you are talking about the upward movement, then what usually you will be able to see is so you have this block has moved up with respect to this one. So this is an upward movement, and similarly you will have the downward movement also. So where you are having the blocks, which is, for example, if you have the block which has moved down. Okay. So here the block has moved down with respect to, and this is along the slip plane, and this is the slip plane which has been here. Okay. So this portion is what we call as an fault plane. And this is your surface expression, fault scarp. And if the movement is along the strike, so this will be the strike of the fault here. This will be the strike, this will be the strike of the fault. So on surface it will be somewhere over here. So if you are having dip slip movement, then mostly the movement has been seen along the dip plane. Either it is the block has moved up or block has moved down. That you will be classifying whether it is a normal fault or a reverse fault. So in normal fault, the block usually moves down, and in reverse fault the block moves up. So upward and downward movement along the dip of the fault plane. So normal fault slip usually has been seen that if you are having steep angle, a moderate to steep angle, usually which ranges from 40 to 70 degrees, and those dip with less than 45 degrees are referred as low angle normal faults. Thrust faults, if the dip of the fault plane is less than 45 degrees, so if you are having, for example, you have the reverse fault, so this block has moved up, So, if this angle of the fault is less than 45 degrees, then they are termed as thrust faults. Okay. So, if greater than 45 degrees, then they are termed as reverse faults. Okay. So, here these two faults, that is your normal thrust and the reverse fault, they will fall under the category of compressional tectonic environment, and this will go as an extensional tectonic environment. So, this is the major difference here. And the active faults, so what we are using is the term active for the faults, then it itself suggests that this fault is having the potential to move in near future. So, as in broad definition, what we take is that the active faults are those faults along which the movement has occurred during last 10,000 years. And if you remember that we have been emphasizing this 10,000 years when we have the Holocene epoch. Likely to occur in near future. So, earthquake is likely to occur on a particular fault in near future, then we will classify that as an active fault, and manifestation of the ongoing deformation or the crustal deformation by displaced landforms on the surface is observed. Active faults are considered to be the source for large magnitude earthquakes in near future, and it provides extremely vital information for seismic hazard assessment. So, that is one of the most important parameter which we require for the seismic hazard assessment of any given region. Now, globally, this has been done in most of the countries which have the regions, seismically active regions, and depending on the user, one can classify this active faults. Okay. So, either you want to restrict yourself to last 10,000 years, that is in Holocene, or you want to classify the active faults for if there is a movement during the older time also. Okay. So, this is an example of a fault scarp here, where you can see, because the displacement is the manifestation of the ongoing displacement or the deformation has been seen on the surface. So, this surface has been displaced along the fault line here. Okay. So, if I have to draw the fault line, it will go something like this. Okay. And this portion which you see is your cliff or the elevated portion, and this is termed as fault scarp. So, if you take a section along this line, say A and B, then you will find that you have a manifestation like this. Okay. So, this is an elevation you have. So, this displacement is along an active fault because young surface has been displaced. Now, this part we will discuss later, whether the fault is dipping in this direction, whereas the fault is either like this or the fault is like this. Okay. If this is there, then this block has moved down and this is stationary, whereas in case of this fault, this block has moved up. This part we will discuss when we are talking about the different type of faults, that is an active faults, thrust faults or reverse faults or normal faults. So, in this case, if this block has moved down and the fault is dipping like this, then this becomes normal fault, and in this case, that is, if I say that case 1 is your normal fault and case 2 is your reverse fault. So, as I told that depending on the users, one can classify the faults. Okay. So, active fault scarps, Holocene active faults, a fault that has moved in last 10,000 years. Late Quaternary active fault, a fault that has moved in last 1,30,000 years. And Quaternary active fault, a fault that has moved in last 16 lakh years. Okay. So, this one can classify based on the tectonic activity observed on the respective faults. So, this is a broad classification of the active faults, but what we are interested in is mostly in 10,000 years, what has happened along that particular fault in last 10,000 years. Further, we can also classify the faults as active, capable and potential active faults within prospective of paleoseismic investigations. Okay. So, around the world, scientific and engineering studies are conducted with an aim to locate, study and characterize surface rupturing faults. Okay. So, this is what is the required data. So, to locate, study and characterize what type of faulting is been taking place, and another associated landforms are the faults. So, such surface faultings are mainly seen associated with earthquake having magnitude greater than 6. These studies range from regional, example for seismic hazard assessment, to local scale, and this is mainly done keeping in a background of the design parameters for engineering projects. In both cases, the input of paleoseismic data comes from detailed site specific studies. That is what we are going to learn about trenching, detailed mapping of active fault, etc. Such studies are conducted mainly to satisfy regulatory status, especially in more populated areas with high rate of seismic activity. And in case of India, we are overpopulated. And in case if we take of the Indian subcontinent, then we are having 3 zones. One is your Andaman Nicobar, another one is that is Sumatra, Andaman Trench region, then Himalayan collision zone and Kutch. And as we have discussed in previous lectures, that the area which were been considered as unstable continental regions have also triggered or experienced earthquake in recent past. That is one year 1993 Latur earthquake and 2001 Bhuj earthquake. So, this is mainly is conducted with an aim to satisfy the regulatory status for the seismic hazard assessment. So, further, regulatory status commonly include specific language that defines active fault. So, this will depend on region to region and countries to countries. So, regulatory status of different countries will have different specific language in which they can define their active faults. The following terms are commonly associated with seismogenic structures: faults, blind thrust, fault related faults, strike slip faults and normal faults, etc. Now, term active characterized by current activity. So, if you have active, then an active fault, that is one demonstrating current movement or action. What is current? Contemporary, historic, Holocene or Quaternary. This is one. Another one is capable, having the ability. A capable fault, that is one having the ability for movement in near future. And third is your potential, capable of being or becoming a potential fault. Okay. So, a potential active fault, that is one capable of being or becoming active in near future. This definition is very much similar to the capable fault. Okay. So, you can have different categorization of the faults, whether it is you want to categorize an active fault, or whether you want to categorize an capable fault, or you want to categorize that as your potential fault. Okay. So, you can have this categories on the active fault map depending on your studies, and that is paleoseismic studies. So, paleoseismic studies will be extremely important in characterizing the faults. So, I will end up with this and continue in the next lecture. We will talk more about the active faults in coming lectures. Thank you so much.